In today's video, we are going to be looking at functions involving e. So e is a number. It's a special number, very similar to pi or the imaginary number I, right? Like remember in geometry, pi is 3.14. When we did that imaginary number this year, that was the square root of -1. Right? So we have symbols that represent these special numbers. So in this section, we're going to be looking at this special number e. E is called the Euler number, although I'm just going to refer to it as e. And I'm also going to refer to it as what's called the natural base. And you'll see what I mean in a few problems what that means. Okay, well, what is e? Okay, if we were in school and I gave you these notes, what I'd have you do is I would have you take these numbers 10, 100, 1,000, 10,000, 100,000, and so on, and I'd have you plug them into this expression 1 plus 1 over n all to the n power. And what you would see happening is if you put in 10 to that expression, so you would have taken your calculator and plugged in 1 plus 1 over 10 all to the 10th power, you would see that it comes out to about 2.593, right? And you would do the same thing with 100, and it would come out to be about 2.7. The same thing with 1,000, you would get about 2.716. But then something starts to happen once you get up to like 10,000, 100,000, a million. You would see that the decimals, when you plug those numbers in, all kind of come out to be about the same value. There's not really much change, right? So if I plugged in, let's say like 100,000, 1 plus 1 over 100,000, all to the 100,000, okay, you would see I get like 2.71826. That kind of keeps going on forever. Those decimals keep going. Right? And if I were to plug in like a million, 1 plus 1 over 1 million, all to the 1 million power, you could see I also still get about 2.71828, that would keep going. So every number bigger than this that you continue to plug in is going to be really, really close to that 2.718 value. And that's what the value of e is. So e is approximately 2.718. Okay, so like when you think of pi as 3.14, right? In this section, e is going to be 2.718. So what we would say is that all of these values in this expression converge to that value. Now, just like pi, e we can't write as a fraction or a decimal because this decimal keeps going on forever. It repeats. It doesn't repeat and it never stops. So we say that e is an irrational number, just like pi. It's irrational, but we approximate it at about 2.718. Okay, so a couple of things that we use e for. We are in our exponents unit, all right? So, you know, if I'm going to simplify the expression using the natural base, so again, natural base is just e, I might ask you to simplify a couple of expressions that have e as its base. Well, what we're really doing in this first example with these three problems is we're just using our properties of exponents. So we're going to use the properties of exponents just like we have before. So if I said, what's e to the third times e to the sixth? Well, I want your answer in terms of e. And if you remember that when you multiply the same base, here we're going to add the exponents. Okay, so e to the third times e to the sixth is e to the ninth, because 3 plus 6 is 9. And that's how you would leave your answer. For letter B, 16e to the eighth divided by 4e to the sixth. All right, if you remember coefficients, those just get divided like normal. So 16 divided by 4 is 4. E to the eighth over e to the sixth. Here you subtract exponents. 8 minus 6 is 2, so this is e to the second. Or if you remember in these kind of problems, this is where I would ask you, where do you have more? Right, where do I have more e's? Well, I have more e's at the top. How many more do I have? I have 2. So my 2 extra e's would be left at the top with the 4. All right, so 4e to the second. Okay. And in my last example, I have 3e to the negative 5x all to the second power. So one thing you'll notice is the x is now in the exponent of your term, which is fine. So we are going to start to see x being in the exponent of our expressions and equations from here on out. So I'm still going to use the same properties of exponents. If I have something that has a power, all to a power, remember power to power means you multiply exponents. Okay, but a couple of things, I want to make sure everything in here gets that power of 2. So 3 goes to the second power, and e to the negative 5x goes to the second power. Well, 3 squared is 9. E to the negative 5x squared. Don't do 5 squared. This is saying negative 5x is an exponent times the other exponent 2. This becomes e to the negative 10x. Right? Because x is now in the exponent, you're multiplying it to the other exponent. Okay, and the last thing about this problem, if you remember, we don't like negative exponents, so you want to make sure you move negative exponents. All right, so the only thing getting the negative exponent is the e to the negative 10x. So 9 is going to stay, and I'm going to move e to the negative 10x down so that it becomes positive 10x. So I have 9 over e to the positive 10x. Okay. Now we're going to do some applications on the second page so you can kind of see where we would actually use e. And in order to do that, I just want to show you how you would plug e into your calculator. All right, so if I wanted you to find like e to the 4th, to evaluate this in your calculator, what you would press right here is you would hit the second key. And then all the way down, it's like the third button from the bottom, you can see this ln key. Right above it, it says e to the x. So if you hit second ln, that automatically inputs your e value. So if I wanted e to the 4th, I could type that in, and I get approximately 54.6. Okay, we are going to have some negative exponents, so maybe you type in, second ln, so e to the negative 0.09. One thing I will say about when you're plugging these in is be really careful. I have a lot of students that forget the 0 between your decimal point. Maybe you forget a decimal point. So there's really, those are some common errors you just have to make sure you're really careful about. Maybe you forget the negative. So that can affect your answer on the next page when we go to do your applications. So e to the negative 0.09 is about 0.913, so we'll say it's about 0.91. All right, and the last one, maybe you have a couple of different values going in. You can type this whole thing in, 2e to the 3rd. You can type that all in as one expression, 2 second ln, e to the 3rd. I can just type that whole thing in, and I get about 40.17, so maybe about 40.2. Okay, so second ln is how you're going to access the value for e to the exponent. Okay, so let's look at a couple of applications. And then you'll be practicing some of this on your Schoology homework. Okay? All right, so applications involving e. So the population of a city can be modeled by the function p equals 125,000 e to the 0.02t. Where t is the number of years since 1990. So if I wanted to know what's the population of the city in 1990, right, we're talking about time since 1990. Well, if I'm talking about 1990, the number of years that have passed since 1990 is 0. You can also think of this as I'm asking you what's the initial population. So anytime I want to know what's the initial value, you're thinking when time is 0, what was the amount that we were talking about? And in this case, we're talking about people. So in my equation, I'm going to replace t with 0. So 125,000 e to the 0.02 times 0. So you can see it's times 0. So you can type that whole thing in your calculator. And I'm going to type 125,000 second ln e to the 0.02, and then I'm going to use parentheses to represent time 0. So you can kind of see how I'm typing that in. You can type the whole thing in. And I'm going to hit enter. And I get 125,000 people. And we're talking about people here. All right? So, there was the 125,000, and there it was in the equation. So remember, last week, when you did that exponential growth and decay models, remember that A value, wasn't that the initial value? Right? Because when x is 0, this b to the 0 kind of goes away. So you do want to plug 0 in for your time if I'm asking you for initial values, but what you should expect is that you are going to get that A value. Right? If I wanted to know what's the current population of the city today, okay, well, how many years have passed since 1990 to 2020? I don't want to plug in 2020 because that would represent 2020 years since 1990. It's only been 30 years since 1990. All right, so I'm going to plug in 30 for T. So P equals 125,000 e to the 0.02 times 30. And again, I can just plug that right in, 125,000 second ln e to the 0.02 times 30. All right, so you can see I just typed the whole equation in. I'm going to hit enter. And I get about, now this is people, so you get about 227,764.85. And if this was a multiple choice question, or I asked you to tell me how many current people were in this city today, we would round that and say it's probably about 227,765 people. Okay, so that's the current population today. Okay, so just be careful when you're plugging in your value for T and looking at time, how much time has elapsed since what they define in the problem. Okay, now in your Schoology practice, any work that I'm looking for, this is what I'm looking for. If you can show me, what you typed into your calculator to get that value, that would be perfect. All right. And the last kind of problem that you're going to see the value of E used for, this is a pretty common problem. Right? And you might see this formula quite frequently. This is called the continuously compounded interest formula. So what that means is if you have money and you invest it in a bank account, we say that the bank can give you interest, like it will pay you money so many times a year if you keep your money in that account, and that's called interest. And when they compound it, that's when they take a certain percent of what you have in your account and they give you that money added towards your account. Well, when we say interest is compounded continuously, that means instantaneously. So as soon as the bank, takes a certain percent of the money that's in your account and they add it into your account, they automatically do it again. And then after they do that, they do it one more time. So that compound continuously formula is given by, I call it like the PERT formula because it looks like it spells out the word PERT. A equals P e to the RT. So A is going to be like the amount that's left after a certain amount of time. So the amount of money in your bank account in the end. T is time, so that's still years. P is what's called the principal, or it's just the initial amount. So that's still your initial amount, but when it comes to bank accounts, we refer to that as the principal. And R is your interest rate expressed as a decimal. So that should look familiar from last week, right? Like when you had rates that you were plugging into your exponential equations, your rates we had to plug in as decimals, right? So just be careful when you're plugging those in, okay? So this is a formula you're gonna wanna use anytime we talk about a bank account being compounded continuously. All right, so let's look at number 4. You deposit $3,000 into an account that pays 3.5% annual interest compounded continuously. What's the balance after 6 years? Well, here's my formula. A equals P e to the RT. Okay, I'm looking for A. I want to know how much money I have after 6 years. The principal is what I started with. So I started with $3,000. E to the R, the rate is 3.5%, but as a decimal, okay, remember we take our decimal point, you just move it over twice, or you divide by 0. So that's 0.035 that I'm going to plug into my calculator or into this formula, 0.035 times the time, and the time period is 6. So this is what's going to be in my account after 6 years. So again, this is the work I want to see on your paper when it comes to the Schoology practice, but then you can just type this whole thing into your calculator, 3,000 second ln, so e to the 0.035 times 6. You can see it's all up in that exponent. If I hit enter, now we're talking money, so I'm just going to round it to 2 decimal places, the nearest hundredth, because we're talking about money, so that makes the most sense here. So I have about $3,701, and we'll say 3 cents. Okay, so after 6 years, you had $3,000, and you now have $3,701.03. Okay. All right. And the last question, all right? So let's say you deposit $2,500 into an account. It pays 5% annual interest, compounded continuously. So I know I'm going to use this PERT formula. This time I want you to estimate the amount of time it takes for your accounts to increase by $1,000. All right, so here's my formula, A equals P e to the RT. Okay, and this time I want to know time. You can see this, I set this up as a multiple choice question. You can see I've got 4 time periods. So I want to know after 3, 5, 7, or 9, how many of, which of those years is going to get me to where my account has been increased by $1,000. So if I kind of fill in what I have, my principal, what I started with, was $2,500. E to the rate here, this was 5%. Okay, so 5% as a decimal. If I take my decimal and move it over 2 places, that's 0.05. Oops, there we go. Okay, so e to the 0.05. Now I'm looking for t. I want to know what time period makes my value of my bank account increase by $1,000. Well, that just means if I started with $2,500, when am I going to end up with $3,500? That's what this was asking. So if you notice, t is in the exponent. You don't know how to solve equations with x in the exponent. Not yet. We will, but right now, you can't just divide by 2,500 and then divide by 0.05. That doesn't work like that because your value of the variable is in the exponent. So if I give you 4 choices, right, think about your strategies for multiple choice questions. Just take these values and plug them in for, we're looking for t, so plug them in for t. And we're looking for what value when you plug in for t gives you out approximately $3,500, right? So if I plugged in 3, I have 2,500. Second e to the 0.05, that's 5%, times 3. If I looked at my account after 3 years, well, after 3 years, I only have about $2,904 and like 59 cents, right? So it's not A, because again, I'm looking for $3,500. All right, so if I do 2,500 second e to the 0.05 times, let's see, 5, what do we get after 5 years? Oops, I used the wrong base. Let me do that again. 2,500 second e, 0.05 times 5. Okay, I get 32. So I'm getting closer, 32.10, about 6 cents. But again, I'm looking for when it increased by 1,000, so I'm looking for 3,500. All right, so let's see what happens after 7 years. 2,500 second e, 0.05 times 7. All right, so after 7 years, there it is. I'm about 3,547, and we'll say that's like 67 cents. Okay, so after 7 years, okay, that's when my account has increased by about $1,000. So again, in Schoology, if I gave you on your practice, if I gave you a problem like this is kind of what I'm looking for. Can you show me, what you plugged in to show me why you picked that correct answer? Okay, if I plugged in 9, You just double check. 2,500 second ln e to the 0.05 times 9. Right after 9 years, I'm up at $3,900 and around $3,900. So, that's why C is our best answer. That's where we got to approximately $3,500. So you have a few problems like this in your practice, so just be careful. I might ask you well, when does your account get to $5,000? So you would actually just put that value in, and that's when you're looking for your account to get to. Maybe I want to know, well, how long does it take what you started with to double? So you think about that number is now twice whatever your principal was. So just pay attention to the wording, and again, if I'm asking you for time, you want to take your answer choices and plug them into the equation that you wrote to see which one produces the value that you're asked to get to.